Yeah, good morning everyone. My name is Florian Meyer, and today I would like to present a joint work with Mr. Volker Turau, which is the development of QMA, a contention-based channel access scheme for the IIoT based on reinforcement learning. And as many of you probably know, contention-based channel access is usually employed by many MAC protocols of the IIoT for the transmission of secondary or management traffic. And unfortunately, especially in very large and dense networks, this secondary traffic often does not provide sufficient reliability to support the primary traffic, in the sense that, for example, transmission slots are not allocated fast enough so that we actually have to drop some data packets of the primary traffic, which is something that we do not want. And luckily for us though, the secondary traffic is often characterized by a bunch of hidden patterns. For example, when allocating a slot, a transmission slot, many management messages have to be exchanged. And a node in the network can actually learn through machine learning these hidden patterns of its neighboring nodes and adapt to them in a way that it learns at which times it's beneficial to transmit a packet and at which times it's not. So that's the goal of this work. When choosing a machine learning algorithm for this kind of application, there are usually two challenges. The first of which is the adaptability to changing network conditions, for example, node failure. So because of that, we cannot choose any pre-trained models. And the second challenge is actually the applicability on resource-restricted devices, which basically means that we have to choose a very lightweight machine learning algorithm and cannot use any deep learning models like deep neural networks. One algorithm that is proven to be quite good in this kind of application is actually Q-learning, which is a reinforcement learning algorithm where an agent interacts with an environment in the sense that it retrieves a state st at time t from the environment and executes an action at in response to it, which then alters the state of the environment. So the environment gives back state st plus 1 to the agent, combined with a reward rt, which indicates how good the action actually was. Now, the idea of Q-learning is to build a Q table, which basically for every combination of state and action holds a Q value, which indicates how good the given action is in the given state. And this Q value is calculated for every state action pair using the Bellman equation, which, as I said, includes the current reward RT, but also includes some kind of metric for the maximum Q value of the next state, which in this case would be 1, for example, if we're currently in state S0. So this allows us to look into the future and see if the next action in the next state is also beneficial for us. This Q-learning algorithm is applied in QMA, which is short for Q-learning based multiple access scheme. And what I brought you here is an example of a frame structure of IEEE 802.15.4 because this is one of the ideal scenarios for QMA. Now, IEEE 802.15.4 features a contention-free period where we have contention-free channel access based on time slots that can be allocated between two nodes, and a contention access period where usually CSMA-CA is employed for contention-based channel access. And this is what we're interested in, because the basic idea of QMA is to subdivide this contention-based period into multiple equally spaced subslots. And these subslots are given as an input to our Q-learning agent. So the only information that the Q-learning agent gets is in what subslot we are currently in. Now, at the beginning of every of these subslots, the Q agent selects one of three actions, which is a backoff action, a CCA action, or a send action. Assuming that we're in state S1, a backoff action would simply do nothing and back off to the next state where the next action is chosen. A CCA does what the name says, a clear channel assessment, so it basically checks if any transmission is going on at the moment. If not, it sends a packet right away, and otherwise it backs off to the next slot where the next action is chosen. The send action simply sends a packet right away without any further ado. Now this gives us a way of prioritizing traffic, because the send action sends a packet immediately, while the CCA action just waits a bit, checks if any other transmission is going on, so nodes can actually build a priority there. Now, The rewards for the different actions are given here. So we decided to split the rewards for the different actions. We have the rewards for the backoff, send, and CCA action here. And the basic idea, as I said, is to learn in which slot it is beneficial to transmit a data packet and in which slots it's not beneficial. So the basic idea is that for a backoff action, for example, we give a high positive reward if we overheard another transmission, because that means that we did not send ourselves and we did not disturb any other transmissions that are going on. Now the send state is a high risk, high reward state, because we do not pay attention to any other nodes in the network, and if it's successful we give a high positive reward, and if it's a failure we give a high punishment. The last state, or the last reward, is the one for the CCA, where we just give a high reward if the CCA was successful and the transmission was successful, and the opposite if the transmission failed. And if we just had a failing CCA, we overheard the transmission of somebody else in the network, so this is good because we did not send a packet right away, so we're giving a positive reward here as well. Now, with that in mind, let's look at some results of QMA. And here I brought you some results for a hidden node topology, which are 3 nodes where the outer 2 nodes cannot hear each other. And in this scenario, we actually look at the packet delivery ratio, because this is a direct indication of how many collisions occur, how many packets fail in this scenario. And what you can see here actually on the x-axis is the number of packets per second. On the y-axis you have the packet delivery ratio, and we expect that in this scenario CSMA-CA performs quite badly, because it relies heavily on clear channel assessments, which often fail because, as I said, the 2 nodes here cannot hear each other. But QMA actually learns at which slots it's beneficial to send, at which slots it's not beneficial to send. And therefore, you can see that at 25 packets it achieves a much higher reliability than slotted CSMA and unslotted CSMA. Now that already brings me to the conclusion. So we can conclude that QMA definitely solves the hidden node problem by providing up to 25 times CSMA-CA's throughput without losing any reliability. What I didn't show you here is we did some experiment in an IoT testbed where we achieved a higher throughput than CSMA using the same energy budget, and in the future work we would actually like to reduce QMA's memory overhead a bit by changing the data representation from float to some fixed point arithmetic, and to reduce the learning time a bit more. And yeah, that's basically it. Now I'm ready for your questions.